So recall when we were looking at integrals in 2 dimensions, sometimes it was easier to work with polar coordinates rather than rectangular coordinates. So in this section, we're going to see two new coordinate systems that help us evaluate some integrals in 3 space. These coordinate systems are going to be called cylindrical and spherical coordinate. So just as I said, here's a recap of what we did in the xy plane. So when we wanted to represent a point in the xy plane, we could use the x units in the x direction and y units in the y direction, or we could use polar coordinates, where we looked at r was the distance from the point to the origin in the xy plane, and theta was the angle from the x-axis to our ray going out. And this r and theta uniquely determined the point as well, and we saw in lots of cases this was easier to work with than just x and y coordinates. So if you recall, we had these relations where x is given by r cosine theta and y is given by r sine theta. And we also made use of the fact that x squared plus y squared is equal to r squared. So these all follow just by creating a triangle from this picture here and using trigonometry. So now what we're going to do is we're going to take these polar coordinates and we're going to extend these into 3-dimensional space. So see here, we still have, think of this triangle here in the bottom. This is in the xy plane. So we go x units over and y units up. And notice our point here is given x, y, z. So in this case, x is r cosine theta, y is r sine theta, and z is 0 because we're in the xy plane. And then if we want a point in 3 space, we can then go up z units, and that will tell us how high above this point we are. So we have the point then r cosine theta, r sine theta, z. And so we can see this point is determined uniquely by r, theta, and z. And so those are going to be our cylindrical coordinates, r, theta, and z. And so let's look at the kind of pictures we get if we fix particular values. Now we know already if we fix z equal to some value, we just get a plane parallel to the xy plane. So let's suppose we fix a value of r. So say r is equal to r0 for some constant r0. What we get then is a cylinder of radius r0. So in this case, we have r equals 2. You can see this is going along the z-axis, centered at the origin, and it has a radius of 2. So one thing to keep in mind from this is since this cylinder is a constant for one of our coordinates in cylindrical coordinates, that means if we're working with cylinders, they're going to be very easy to work with if we're using cylindrical coordinates. Because we have a nice equation here. This is described just by r equals 2. Whereas if we were in the if we were using rectangular coordinates, we'd have to use that equation as x squared plus y squared equals 4. And so that's a bit of a bigger pain when we're setting up limits of integration. Now if we fix the value of theta and just look at theta equals theta 0, we obtain a half plane that starts at the z-axis. So we can see here this is along the z-axis, and then it just goes out in this direction. So this is a little small to see here, but this is where theta is equal to pi over 4. So you start at the origin, you just go out pi over 4. It doesn't go in both directions because the other direction would be a different value of theta. So again, if we're just looking at half planes, the cylindrical coordinates will be quite nice to work with. So cylindrical coordinates are really not that different than what we've been used to because we're already used to polar coordinates, and all we're doing is adding a z value to the polar coordinates. So that's really not anything particularly new from what we've looked at before. Now spherical coordinates are quite a bit different than what we've been using before. So in this case, rather than going a distance out in the xy plane and then a distance up, we're going to go straight out from the origin to our point. And so we're going to have a distance from the origin, which we're going to denote as rho, and then we're going to have 2 angles to determine the point. So you see we go out here a distance of rho to get to our point, and now theta tells us how much to rotate this in the xy direction, and phi tells us how far down to go from the z-axis. So we can think of, we start off by, if we're constructing this point, we can think we go up a distance of rho to get to our point. Phi tells us how far down to go from the z-axis to get to here, and then theta tells us how much do we rotate in this direction to get to the point. So those 3 pieces of information, rho, phi, and theta, is enough to tell us exactly where this point is. Now, rho starts at the origin and goes out, So rho is always going to be bigger than or equal to 0. And theta we know can go all the way around. This is the same theta we were using before. So theta can go from 0 to 2 pi. Now, if we want to determine the point uniquely, we only want our phi to go from 0 to down to the negative z-axis, so from 0 to pi. And we don't want to go through, because if we go through, we're just going to want to think of that as rotating our theta around to get to a point on this side. So we have rho bigger than or equal to 0, theta is between 0 and 2 pi, and phi is between 0 and pi. And just like before, where we wanted to see what happened when like r was a fixed constant, theta was a fixed constant, we want to do the same thing here with our rho. Theta we already know, and then with phi as well. So our first and easiest case is when we fix rho to be just rho 0. In this case, we obtain a sphere of radius rho 0. So here we can see this is a sphere centered at the origin, and the rho here is 2, so it has a radius of 2 in every direction. So as you might expect, since we call them spherical coordinates, spheres are particularly easy to work with in spherical coordinates, while they're particularly a pain to work with in rectangular coordinates. We already saw that if we fix theta, we get a half plane. So now let's look at the other variable, phi. So what happens if we fix phi to be phi 0 for some constant phi 0? Well, in this case, we're going to get a cone. So remember, we're measuring down from the z-axis, which would be going up here, and we measure down phi to get an angle of pi over 4, and then we get every value that satisfies it's on phi equals pi over 4, so everything on this cone we can rotate all around to get all of these points. So again, cones will be very nice to work with in spherical coordinates as well. So now, of course, what we want to do is we want to be able to work between these coordinate systems. If we want to be able to transfer different types of integrals and limits, we want to know how we go back and forth between these. So recall, we can just use the coordinates we already had for polar coordinates, where we know x is r cosine theta, y is r sine theta, and then our z value is just z, so that's not doing anything new. And then we have r squared equals x squared plus y squared. So this is how we can relate rectangular and cylindrical coordinates. So that's pretty easy to do. We've already done all the hard work when we did polar coordinates. So the spherical coordinates are a little bit more difficult to do. So let's look at a picture for the spherical coordinates again. And we want to relate this to, first we'll do polar coordinates. So obviously the theta is still theta. And now let's think of what's going on here. So if this angle here is phi, think of taking this z and transferring it over here. So this distance here will make a triangle across here like this. So this height here is z. So by trigonometry, z should be rho cosine phi. And then think of the r goes across here, so it goes a triangle like this. And so the r should be rho sine phi. Just think of creating that triangle there. So we get these values. And notice we also, using that triangle again, we have a right triangle here. So the hypotenuse is rho, this side is z, this side is r. So we get, or you could use this triangle here as well, rho squared equals z squared plus r squared. So we get these things. Now, of course, we could go back and do everything here in terms of rectangular coordinates, but we can also just use our earlier conversions. So we know that x is equal to r cosine phi, but we just saw r is rho sine phi. So just plug this in for r, and we get x is rho sine phi cosine theta, and y, which is r sine theta, is rho sine phi sine theta. Just replacing the r again. And then z we already saw is rho cosine phi. And then if we replace the r squared with x squared plus y squared, we get rho squared is x squared plus y squared plus z squared. So that gives the conversion here on this page, gives you everything you want for converting between rectangular, spherical, and cylindrical coordinates. And here's a picture again. And now we filled in the x, y, and z coordinates in terms of rho, sine, and phi, and we can see the z and the r labeled here in this picture. Now, when we were doing integrals in polar coordinates, remember we had to figure out what does a little incremental area look like in polar coordinates. Well, we took a little incremental area like this, and we said the arc length here, we use the formula for arc length. So if we're out a distance of r, and we use a change of delta theta in the angle, then this arc length is r delta theta. And we know that the distance here is a change in r is delta r. So while this doesn't look like a rectangle, because I've blown it up to be fairly large to make the picture easier to see, if we let delta theta and delta r get smaller and smaller, this gets closer and closer to a rectangle that would have side length r delta theta and delta r. So we get the area is approximately r delta theta. So we saw that when we were doing polar coordinates. Now what we need to do for our new coordinate systems with volume is figure out what does a little slice of volume look like in this case. So here's our picture for a little slice of volume in cylindrical coordinates. So notice the area at the bottom here, we can still approximate that was r delta theta delta r, but now this box has a little bit of height delta z. So the volume of this thing should be approximately r delta theta delta r delta z. Here's a picture a little bit larger. And so delta v here is about r delta z delta r delta theta. You can change the order, but this is the order you usually end up using. And so our dv, as we take limits here, is just going to be r dz dr d theta. And so that's our, when we set up integrals in cylindrical coordinates, this is our dv that we're going to want to use. And now the last thing we need from this is we need the volume form for spherical coordinates. And this is a little bit messier to do. So here is our picture. This looks kind of messy, but so here we have our delta phi is coming down here. This is our rho going out. So this distance from here to here is delta rho because it's the change in rho. And now this distance is rho, how far we go out, and then the delta phi, how much we're changing our phi going down. So the only thing we need is this distance here. So if we project this down into the plane, this is still r delta theta that we had before. And then remember, r is rho sine phi. So this distance here is rho sine phi delta theta. So this whole box here should have volume delta rho, rho delta phi, rho sine phi delta theta. So if we put all those together, we get that this is about rho squared sine phi delta rho delta theta delta phi. And you can change the order of these depending upon the integral we're looking at. But then we see if we take the limits here, our volume form we're going to want when we integrate in spherical coordinates is rho squared sine phi d rho d theta d phi. And so those are the things we're going to need to be able to set up integrals in cylindrical and spherical coordinates. And we'll see often this is very useful for evaluating integrals when we have spheres, cylinders, cones, things like that as our boundaries of our regions of integration.